In this example, we're going to use the conservation of mass for one of its more frequent or popular applications. So once again, here's the conservation of mass for a differential element. And the question we want to answer is, let's imagine that we have some steady, incompressible flow whose velocity field is given by this set of equations. We want to know, is it a valid flow? Now, why would that be something that we do? Well, perhaps we went and conducted some experiment and we measured with a probe the velocity field. So we moved and we got velocity points all over the place. Maybe this is some sort of a box, and we put the probe there and we got some value of velocity, and we put the probe here and we get some other value of velocity, and we get the probe here and get some other, and so on. And if you swept over this whole box with our probe and get all sorts of different velocity vectors, I'm just making these up, by the way, I have no idea what the picture should be, but you get some field, and the question is, did we get good data, or was there some error made in our instrumentation? And so we got all these values for local things. You could do some sort of curve fitting that would give us these equations that match these values. And the question is, did we get it right? And so one way of answering that is to ask a slightly different question, which is, does it satisfy continuity? Does it follow the law? And just a refresher, all of this put together can be thought of as our velocity field, right? The velocity vector, which looks like ui plus vj plus w k hat. So let's set about answering that. First, we're going to start with the most general form of the equation, d rho dt plus d rho u dx plus d rho v dy plus d rho w dz, and this has to equal 0 for the law to be followed. Let's apply as many simplifying assumptions as we can. First off, it's steady. That lets us get rid of this term. Second off, it's incompressible, which means all of the densities now cancel out, thanks to it being incompressible. And so the version of this equation that we need to solve is slightly simpler. We just need du dx plus dv dy plus dw dz to equal 0. And so we're going to put a little question mark there and say, does it? Well, we're given our velocity field, and so all we have to do is sub it in and follow through with the math. So I'm just going to take these down here, right? We got a d by dx of what? Well, of u. U is, for this flow field, x squared plus y squared plus z squared. We have to add to that d by dy of v, which was given to us here as xy plus yz plus z squared. And then we have our last term, which was dw dz, d by dz of w. Well, ran out of room there. Hang on, I'm just going to move this to the next line. Excuse my spacious handwriting. Plus d by dz of this thing here, which is minus 3xz minus z squared over 2 plus 4. Okay, so we subbed it in. Now we just do what the math tells us. What is the derivative of this first term with respect to x? Well, d by dx of x squared is 2x. D by dy, or d by dx of y squared is 0. D by dz, or excuse me, d by dx of z squared is also 0. So the first term is just 2x. Second term here with respect to y. D by dy of xy looks like x, excuse me. What have I done? X. D by dy of this second term looks like a z. D by dy of the third term here, z squared, that's just 0. Now we've got to take the derivative of this last thing with respect to z. So this first term here has a z on it, so that's a minus 3x. This second term is z squared over 2, so that's minus 2z over 2, over 2, which you can recognize as just a z. And then this 4, the derivative of that's with respect to 0. Oh, and all of this, what we're wondering is, does it equal 0? So let's real quick look at this. Over here we have 2x plus x, that's a total of 3x's, and here's a negative x, so those cancel. And then with z, we have a positive z there and a negative z here, because 2 over 2 is a 1, and so those are also 0, and so the answer is yes. In other words, we did it right.